Okay, so what I'm going to do is, this is going to be part 2, and we're going to pick it up on this document I'm about to share. Right. Where is it? Here it is. There we go. Now this is where we, excuse me, this is where we left off. I've already posted part 1 with all the questions up to this point. And now we're going to look at starting with 180. And of course, you probably already know they're not in sequence. So we're going to go from 180 and then skip to 204. All right. So 180. Question is, when we look at this molecule, and how many carbons do we have? 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. This one's got a nitrogen on it. This one's got 2 hydrogens. This one's got an oxygen. This one's got a hydrogen. This one's got a double bond and 2 hydrogens. Okay, this is an organic molecule, but we can still apply the VSEPR model to it. It just, organic chemistry has some conventions that may throw you if you've never seen it before. And I'll just remind you, I may have said this before, probably have. Whenever a hydrogen is next to a carbon like this, right behind a carbon, those hydrogens are bound to that carbon. They're not bound to the other carbons. They're bound to this one. So it would be like that hydrogen would be here. These 2 hydrogens would be like that. These 2 would be like that. And one other thing I'll call your attention to, whenever you have carbon in an organic compound, most of the time, there are exceptions, most of the time, there will be 4 bonds to that carbon. So here we have 1, 2, 3, 4. Here we have 1, 2, 3, 4. 1, 2, 3, 4. 4 bonds to each carbon. But to answer this question, we need to look at how many lone pairs and bonding groups are surrounding each carbon. Because the question says, what is the hybridization of each carbon atom? Right? So this is 1, 2, 3, 4, 5 in sequence. All right. So how many groups do we have around this one? 1, 2, 3. There are no lone pairs. Right? If you see 4 bonds, then there's no lone pair around carbon. So this one has 3 groups. I'm just going to mark off the groups first. This one has 3. 1, 2, 1, 2, 3 here. 1, 2, 3 there. 4 there. And 2 here. So those are the number of electron groups. And remember what we said about hybridizing S and P orbitals. You need 3 of them here. So that's 1 S and 2 P's. Same thing for here. 4 of them here. So that's an sp3. And 2 of them here is just sp. Okay? So let's see which one. You need 2, 2, 2, 3, and 1. 2, 2, 2, 3. Looks like it's A. That one right there. Wow, this is not cooperating with me. Let's try it this way. There we go. So that would be the hybridization for each carbon atom in this sequence. Now, just out of curiosity, what would be the hybridization on oxygen and nitrogen? Well, to do that one, you need to know the lone pairs. And oxygen has 2 lone pairs. All right. And let's see, does that give it an octet? Well, yeah, 2, 4, 6, 8. Here we have 2, 4, 6, 8. Now we could go and draw the Lewis dot structure for this whole molecule and end up at the same place, but it's quicker just to say needs an octet, needs an octet. And nitrogen and oxygen are unlikely. Actually, they can't exceed their octets because they're in group 2, right? They don't have access to Ds. Carbon doesn't have access to Ds either. So you can't hybridize a carbon into a trigonal bipyramid or an octahedron. It doesn't have any Ds to hybridize with. So this is as high as you can go with carbon, sp3. All right, any questions about that one? And I'll slide down to 204. All right. Okay, which of the following statements best describes the Heisenberg uncertainty principle? What does the Heisenberg uncertainty principle talk about? It talks about two things. Where is the particle located and how fast is it moving? Now, in technical terms, it's not really talking about just the velocity, but it's talking about the momentum, mass times velocity. But the particle is not going to change mass in the middle of a measurement. So we're really talking about its velocity. You can't know for small particles like electrons and atoms for that matter. You can't know exactly where it is and how fast it's going at the same time. But if you know how fast it's moving, right, you know its momentum, you can't know where it is. That's what Heisenberg said. Let's see which one of these statements matches that. Let's see, it's impossible to accurately know both the exact location and the momentum of, well, there it is, right there. That's the answer. Just for fun, let's look at these others. The exact position of an electron is always uncertain. No, you can know it. You just can't know how fast it's moving. You don't know its momentum. The velocity of a particle can only be estimated. No, you can say how fast it's going. You just don't know where it is. That seems weird, doesn't it? You can measure the velocity of something, but you don't know where it's located. The location and momentum of a macroscopic object are not known with certainty. Well, actually, the mathematical expression for Heisenberg's uncertainty principle is actually related to the mass of the object. As objects get larger, then the uncertainty principle fades away. So the larger the mass, the less uncertainty there is in measuring both position and momentum at the same time. So an object as big as I am, yeah, you can know where I am and how fast I'm going because I've exceeded the limits of the uncertainty by my mass. For something that's really, really, really small, like a molecule, an atom, or electron, or a subatomic particle, that's where the uncertainty principle really hamstrings the observer. So D is false also. The location and momentum of a particle can be determined accurately, but not the identity. I think we were just running out of things to put in there as alternates because E is rather ludicrous. I can know the identity of the particle. Whether I measure its momentum or its location, it doesn't matter. I know what it is. That's not to say there's not some other principle that would address that situation, but as it is, Heisenberg's principle says nothing about that. Okay, that was 204. Oops, went too far. 208. Okay, Mendeleev. Remember Mendeleev? The first really useful periodic table. He's given most of the credit for the development of the periodic table because, well, let's see, what are our choices? His periodic table is arranged in octaves. I don't think so. That sounds like music to me. Well, octaves just means groups of 8. So that's not it. B, he had the longest history of research in elemental properties. Now, there were scientists that were in the business a lot longer than Mendeleev. Mendeleev was a teacher. I mean, if he did any research, it was kind of on the side. His primary source of income was teaching. So that's not it. He emphasized its usefulness in predicting the existence and properties of unknown elements. There. That's it. C. He used the table to predict both the existence of elements and what their properties would be. His representation, so C is really the answer. Right there. His representation of the table was the most understandable. Not in the beginning. Remember, in the beginning, his periods went up and down, and his groups went side to side. So he in his second publication, he rotated it 90 degrees. He grouped elements into triads. Now that wasn't Mendeleev that did that. I think that was Dobereiner that came up with the triads. And Mendeleev just built on it. The triad scientist, whoever that was, just kind of dropped the ball. He wasn't interested any further than just the triads. But progress in science is made in baby steps. Rarely do we have massive discoveries. Now, not that they don't happen, but that's not typically how we progress in the sciences. It's usually by baby steps, and then we'll make. In fact, the baby steps parse what we know into smaller and smaller groups of information, and they separate from one another. So they kind of go their own separate ways. The real progress in science is made when somebody with a presence of mind takes all those little bits that have been developed over the decades or even centuries, pulls them all together into coherent, understandable explanation. That's what Linus Pauling did with his publications on the nature of the chemical bond. Those are the synthesizers. Most scientists are analyzers. They tear things apart and look at them. But occasionally you'll get a mind that will synthesize, will bring things together. And Pauling was one of them. Okay, that was 208. How about this one? Nitrogen has 5 valence electrons, 226. Nitrogen has 5 valence electrons. Which of the following electronic configurations represents the ground state of the N- ion? Okay. First of all, what do we mean by ground state? Ground state doesn't have to be limited to neutral atoms. The ground state means lowest possible energy for all the electrons. Right? You can't have any electrons promoted to higher levels in an excited state. They always have to be at the lowest. That means you fill them up from the bottom up, and you don't skip anything. All right, so let's do the electronic structure for nitrogen. It has 5 valence electrons. Well, let's do all of them. It's got 7 electrons total. So it'll be 1s2, 2s2, 2p, 3, right? 3, 5, 6, 7. So we're talking about these right here. That's what's in the picture. Notice that the p orbitals, they still have 3 suborbitals. Okay? So this s orbital would be like that. Okay? Exclusion principle. And these 3 would be like that. Correct? Now, what about n minus? That means we've added an electron. So where does the electron go? Well, these 3 are half filled. So now we can go back and start pairing them up. Like that. So this one will look like B. No, because 2s doesn't have any in it. 2s needs 2 in it. There we go. E. Right there. Have 2 here, 2 there, and 2 unpaired. So what does that mean for the response of this ion to a magnetic field? Is it paramagnetic or diamagnetic? Remember, the diamagnetics had no response to the magnetic field, or they're repelled by it. The paramagnetics are attracted to the magnetic field, and they need unpaired electrons in order to do that. So this explanation gives you those unpaired electrons, right? So this will explain. Now, if we were to do, well, molecular orbitals don't make any sense here because it's not a molecule. It's just an independent nitrogen ion. Okay, so that would be E, option E. Okay, let's scroll just a little bit. And we do all 3 of those without having to move the screen. 227. An element has the electronic configuration. It looks like this is the shorthand version, right? Because we've got argon, and you don't have to, but I'm going to 18. I'm going to put 18 here for argon. And then the rest of the, now where does this start? This starts just past argon, right? So that would be potassium. Potassium, calcium, as we add electrons. And we have 3 Ds, 10, and 4p2. So the element is in which group? All right. Well, we know that if you're filling the p orbitals, you're in this side right over here, right? So if we start with argon, you go back over here to 4, and then 3d10 is full, right? D orbitals can have 10 electrons, so it's full, it's crammed. Then the last 2 go into here. So if we start here, 4p1, then 4p2 is germanium, right? Germanium. All right, where is germanium in that chart? Well, it's definitely in the p orbital filling, but is it a metal or a non-metal? Right? Or Actually, if the choice is there, could it be a metalloid? Right? Remember where the dark line goes. Let me get a little closer. Right under boron, then it stair steps down like that. Top of germanium to the right, between germanium and arsenic, is that line. So germanium is a metalloid, which means under certain circumstances, it behaves as a metal. Under other circumstances, it may behave as a nonmetal. So the best answer is E. It's a metalloid. Right? It's also a metal, but when you're in a multiple choice situation, you pick the best answer. And the best answer is the metalloid because of where it's located. All right, that was 227. 231. In which group do all the elements have the same number of valence electrons? Okay, so what you have to do, now, how do we know the number of valence electrons? Well, the old style of numbering the groups with Roman numerals was extremely useful because from left to right, Roman numeral 1, 2, 3, 4, 5, 6, 7, 8. That's the number of valence electrons in that group, right? It skips over the transition metals. The transition metals do have some Roman numerals, but to differentiate the representative elements from the transitions, we have 1A, 2A, 3A, 4A, and down here we have Bs. So actually, do we have any? Cadmium, silver, yeah, and there's argon. Well, these should be easy to eliminate, right? If we see argon here, what other elements should be in that with it? Noble gases only. Nothing else will do. Silver and cadmium, that makes A false. Okay? So A is false. How about B? Sodium, calcium, barium. Sodium is an alkali metal. Calcium and barium are alkaline earths. Alkali metals have 1 valence electron, earths have 2. Right? So B is false. Can't be. How about phosphorus, sulfur, and chlorine? Well, phosphorus and sulfur and those are all three in different groups. Right? Phosphorus is here, sulfur, and chlorine. So the tricky part about that question is you have to know that the valence electrons depend on the groups, not the periods. The periods, you're actually adding valence electrons from left to right. So sulfur has 1 more than phosphorus, and chlorine has 1 more than sulfur. So C is false also. How about D? Phosphorus, arsenic, selenium. Okay, let's look at our chart. There's phosphorus, there's arsenic, oops, selenium to the right. That has 1 more than arsenic. It actually has 1 more valence than phosphorus. So that one's false also. So what is the E choice? 231. None of these. E is the best answer. None of them have the same number of valence electrons because none of them are all in the same group. All right, that was 31. Let's go to 36. Okay, which of the following was not an elemental property usually predicted by Mendeleev for unknown elements? What type of things did he predict? Well, He predicted whether it would be metallic or non-metallic. He predicted its density. He used that also. He predicted chemical properties like, well, let's finish with physical properties. If it was a liquid, he predicted the boiling point. If it was a gas, the condensation point. If it was a solid, the melting point. He predicted those also. Chemical properties. He predicted reactivity. Right? How would it react, this unknown element? Well, generally speaking, it would react similar to the ones in the group where he placed it. So the halogens react a certain way, and the pnictogens would act a certain way, so forth and so on. So which one of these did Mendeleev not predict? Let's work from the bottom up. Oxide formula. Oxide formula was bread and butter to chemists of his day. They knew elements by the oxides that they formed. Thus, the chalcogens. Anything that formed, well, no, the oxygen, I misspoke. They would form, the elements would form a calx. That is a combination with oxygen. And you can see it on fertilizer bags today. I mean, if you go to Lowe's or any seed store and look at a bag of fertilizer, what will it list on it? It'll have the percent nitrogen. It'll have the percent phosphorus, and it'll have the percent potassium. NPK is standard analysis for fertilizers. But notice, nitrogen is the pure element percentage. But phosphorus is given as the percentage as P2O5, and potassium as K2O. Those are the oxides of those elements that we inherited from history. Okay, so let me get back to the point. He did predict oxide formulas. That's true. Boiling points, yep. Densities, oh yeah. Atomic mass, most certainly. Electronic configuration, no way. Electronic configurations, Mendeleev predated electronic configuration. We're just starting to get a handle on it. It had not worked its way through the scientific community at this time. So A is the one that he did not predict, electronic configuration. We can do that now, right? And he didn't realize it at the time, but the electronic configuration is how the table is organized at this time. And he started that organization back then before he knew it. Okay. 236, let's see. Let me keep up with my hard copy here. 256. Okay. There we go. Which of the following statements is always true concerning a reaction represented by the following balanced chemical equation? So what do we have here? C2H6, right? That's ethane. It's an organic compound. So you wouldn't know that one. Unless you're just really curious and I already looked it up. So this is I better put these in here also. The phases, gas. This is a combustion, right? Anytime you react something with oxygen, we can call it a combustion. Water taken as liquid must be standard state, and carbon dioxide. Okay, so for that equation, what can we say? We've got an option down here that says none of these statements are true. So we have to look at all of them. But actually, we only need to find one that's true, and then E is out. So A, if we have equal masses of C2H6 and O2, there is no limiting reactant. All right. So how are we going to answer that question? Well, let's do it by moles, right? If you have 2 moles of this, what would that mass be? Correct? C2H6. So 2 carbons and 6 hydrogens.
Call from LD.
Okay. So we got 12.01 for carbon times 2, and then 6.06 for all the hydrogens. So that's 30.08. Grams per mole. Okay? So let me write that up here. 30.08 grams per mole. This one is 2 times 16. 32 grams per mole. How about water? Right, we've done that often enough. That's 18.02 grams per mole. And carbon dioxide. 1 carbon is 12.01, correct? And then 2 oxygens, same as that, 32. 44.01. Okay. So A says if we have equal masses of C2H6 and O2, there's no limiting reactant. Equal masses. Right? So what actually determines the limiting reactant? It's not the mass ratio, it's the mole ratio. So in order for these to be stoichiometric, which is what A is asking, you would need a ratio of 60.08 grams and 7 times 32. 224. All right. So that mole ratio of 2 to 7 gives you this mass ratio, which is stoichiometric. So if they have equal masses, it can't be, I mean, they can't be, one of them is limiting if they're equal masses, right? If they're equal masses, if they're 224 over here, same as that one, if this were 224, then that would be limiting because this would have plenty. It would have way more than you need. But if this one were 60.08, right, you wouldn't have enough. Excuse me, you would have, let me see, if you have 60 here and 60 there, 60 requires 224. So this one's going to run out. If you have 224 over here and 224 over there, then you've got excess here, and that one's limiting. Right, right, both. It's limiting, the same one's limiting for each instance. All right, so A is false. Can't be. If we have an equal number of moles of C2H6 and O2, there's no limiting. Well, if we have equal number of moles, the mole ratio is 2 to 7. If you have equals, if you have 2, 2 or 7, 7, one of them is going to be limiting, right? This is the stoichiometric ratio. If you have 7 moles of oxygen and 7 moles of ethane, then you've got excess ethane. If you got 2 moles of ethane and 2 moles of oxygen, then oxygen's going to run out because you need 7 of them. All right, so B is false. How about C? If we have more mass of C2H6, then O2 must be limiting. Okay. If we have more mass of C2H6, more mass than what? Well, more mass than oxygen, obviously. If we have more mass than that, of that, say we have 225 grams, right? You only need 60 of them, and oxygen is limiting. C is true. What if we have more mass of oxygen? More mass of oxygen than, say we have 61 grams, right? Well, oxygen is still limiting. You don't have enough to use up all of that, right? So ethane's not limiting here either. So C is the answer. Oxygen is limiting under those circumstances. All right. How about 261? Which of the following is paired incorrectly? This should be fairly easy. We're talking about strong acids, weak acids, strong bases, weak bases. Right? H2SO4. Is that a strong acid? Yep. Now, it's strong for the first proton. Right? Remember how acids dissociate. Like that. That's a strong acid. If this becomes another acid, right, you dissociate this one, that's a weak acid. Because the second and third protons are they don't dissociate as easily as the first one. Very simple. You got a negative charge over this whole group, and you're trying to pull a positive away from it. The electrostatics there working against you. So A is true. It's a strong acid. How about B? HNO3. Weak acid. Oh, that's another strong acid. How about, what's this next one called? Is that a strong base? Remember, all the alkali metals and alkaline earths form strong bases. In chemical terms, now I believe this one is completely soluble. But whatever goes into solution completely dissociates. That's a strong base. So that was true. How about D? HCl? What is that one called? Hydrochloric acid, right? No oxygen, you start it with hydro. Hydrochloric acid. That one's strong. How about E? NH3, weak base. That's true. What do we mean by a base? The Bronsted-Lowry definition of a base is a receiver of protons. So this receives a proton to make, well, actually it comes from water, and that makes ammonium plus hydroxyl. That's why it's a base, because it forms the hydroxyl. But how much of that goes over here? The attraction for ammonia to the hydrogen ion from water is very weak. In fact, 99.5% or 99.4% of ammonia in solution is still ammonia. That's why when you open the cap of a bottle, on the bottle of ammonia, household cleaning solution, you smell that ammonia right away. It has a very high vapor pressure. So it doesn't form that ammonium easily, which means it's a weak base. So the only one that's false is nitric acid. Okay, let's see, I'm still centered. Okay. 266, 67, and 68 are based upon this premise. An aqueous solution of barium chloride and silver nitrate are mixed. It even tells you what the products are. You really don't need the products because this is a double replacement reaction. So barium chloride right? Barium is a 2+ charge, chloride's a -1. In aqueous solution is mixed with silver nitrate. Which is also aqueous. Okay, and what does it yield? Well, silver goes with the chlorine and barium goes with the nitrate. Correct? Nitrate is a -1, barium is a +2, so you need 2 nitrates. And you have to use a parentheses because nitrate is a polyatomic ion. Okay, so what is it saying? The balanced molecular equation. 67, the balanced complete ionic. 68, the net ionic. So we got to do all 3 of them. Got to balance the equation, molecular, then make it ionic, complete ionic, and then make it net ionic. All right, so do you want to use a budget? We don't have to, but we can. Right, where you put barium here, chlorine, silver, and nitrate. Right? Nitrate's the same on both sides, so we can use it as a balancing group. So on this side, you have 1 barium, 2 chlorines, 1 silver, 1 nitrate. And on this side, you have 1 barium, 1 chlorine, 1 silver, and 2 nitrates. Okay? So, how about chlorines? How are we going to balance those? Well, we need two of them over here, don't we? Two chlorines, right? So that makes two here and two silvers. Okay. So now we need two silvers over here, don't we? There we go. Two silvers. That makes two nitrates. 1, 2, 2, 2, 1, 2, 2, 2. We're balanced. That's the molecular equation. Now, if you do these double replacement reactions are really easy to balance, even without the budget. They're very well behaved, as you might say. All right, so let's see. The balanced molecular equation contains which of the following terms? And notice that they're including coefficients. So if the coefficient's not right, then the answer's not right. So barium chloride. Barium doesn't have it. 2 silver nitrates. 2 silver nitrates. Doesn't have it. 2 silver chlorides. Oh, we forgot to do the phase. Right? These are aqueous. How about silver chloride? Right? You look it up in your chart. Silver and chloride together are solid. How about barium nitrate? All nitrates are soluble. Most chlorides are soluble, except for 3. Silver's one of them. Okay, so 2 AgCl solid is this one. Oops, sorry. There we go. Silver chloride. So B is the answer to 266. Now, balanced complete ionic equation. How do you do that? Well, in solution, barium chloride is not like that. It breaks apart into its ions. So you have a barium 2 plus ion in aqueous solution. And you have 2 chlorides in aqueous solution. Okay? You have 2 silvers in aqueous. And you have 2 nitrates in aqueous solution. How about the solid? Can't touch it. Stays the same. And then barium nitrate is also soluble. So we have 1 barium in solution and 2 nitrates in solution. There you go. That's your complete ionic equation. Now let's see. Ba2 plus. Yeah, it's there, but it's got a coefficient. That doesn't work. There's only one of them. How about 2 chlorides? That didn't work either. How about 2 silvers? Yep. Right there. Nitrates? I got 2 of them. Right, so that can't be. And the last one, silver chloride aqueous. That can't be either. It's a solid. Right? So the only one that works is C. C is the answer. This one right here. So this one related to 266. This one was 267. Now 268. How do you do the net ionic equation? You look for common elements on both sides. So we've got a barium here and a barium there. Aqueous solution, equal amounts. 2 nitrates. Those are spectators. So now our reaction is 2Cl minus plus 2 silver yields 2 silver chloride. Right? All right, if we leave it just like this, then we're going to find that barium and nitrate are both spectators. They're not in the net ionic equation. There's no acid here, and the silver chloride is a solid. So really the only one that you have available to answer that question is this one. 2 silvers right here. But when we write, that's the best answer. A better answer would have been 1 silver. Why? Because 2, 2, and 2, you divide the whole thing through by 2, and you get 1 chlorine, 1 silver, and 1 silver chloride solid. But as written, that's your best answer. This might be the last page, actually. So, even with all that mess I had to go through earlier, and you had to wait through, we might just finish this today. Okay. 279, unless it takes a while to do the calculations. All right. 279. You're holding 2 balloons, an orange balloon and a blue balloon. Well, before we do that, let's find out if there's a difference in size so I can draw them correctly. The orange balloon is filled with neon gas, and the blue balloon is filled with argon. The orange balloon is twice the volume of the blue balloon. So orange right? This is orange. This is blue. Now we can go back. And the volume here, if this is V1 and this is V2, we know that V2 equals 2 times V1. It's twice the volume of that one. Let's go back. The orange balloon is filled with neon. Okay. And the blue balloon is filled with argon. Okay. Which of the following represents the mass ratio of neon to argon? So it should be mass of neon ratio to the mass of argon. Like that. Okay. What does Avogadro say about this situation? Well, we have to assume that the temperatures are equal and the pressures are equal. Pressure is a little easier to handle because if they're both balloons in the atmosphere, it's the same pressure, but it's also the same temperature if they're equilibrated with the environment. All right. So what does Avogadro say now? If they were the same volume, they'd have the same number of particles. But this one's twice the size of that one. So the moles of this one are 2 times the moles of that one. And this is argon. And this is neon. Moles of neon. Okay? So the ratio of neon to argon here by moles is twice as much argon as neon. How about the mass? Well, you have to look at the molar mass to make a prediction there. Neon molar mass is about 20. And argon molar mass is about 40. Right? So, oh, and we're ratio mass. Give me just a second. I'll be right back. Back. Sorry about that. 1, 2, 3, 4, 5. Got the same number of people. Oh, all right. So let's go back. What we're trying to do is say something about the ratio of the mass of neon to the mass of argon. Actually, that's wrong. This is the smaller volume. Right? So this volume is going to have twice the moles of that one. So actually it goes the other way. This is twice as many moles of neon as there are argon. No, that's right. The neon number of moles is twice the argon number of moles. I had it right the first time. Okay? So, if we've got twice as many moles of neon, let's just use an example. Say we have 1 mole of argon. So how many moles of neon are we going to have? 2 moles, right? Twice the volume, twice the moles. Now, 2 moles would be equal to 40 grams. One mole of argon is equal to 40 grams. So this is 1 to 1. Okay, so that makes A the best answer. All right. How about 283? Okay. A 45-gram sample of a metal is heated to 95.2 degrees. This looks like thermochemistry to me. Calorimetry to be exact. And it's placed in a calorimeter containing 100 grams of water at 21.6 degrees. The final temperature of the water is 24.5 degrees Celsius. What metal was used? Based upon what? The specific heat capacity of the metal. So we've got to calculate what is the specific heat capacity of this metal. Right? So remember what we said about calorimetry. The calorimeter is an isolated system. Nothing crosses the barrier, not energy, not matter. So what goes in the calorimeter stays in the calorimeter. Okay, so that being said, all the heat changes that occur inside the calorimeter have to add up to 0. That's it. That's all we need. We just need 1 for the water and 1 for the metal. Right? There's 1 for the metal and there's 1 for the water. So what is Q equal to? Specific heat capacity. Here they're using the small letter C. I think in our textbook it's S. So C times the mass, specific heat capacity times the mass times change in temperature. Okay. Remember, the change in temperature is always final temperature minus initial temperature. So let's put the values out here. What values are we given? Well, for the metal, we've got 45.9 grams. And for the water, we're given 120 grams. Okay? Initial temperature. Initial temperature of the metal is 95.2 degrees. C. And the initial temperature for the water is 21.6. Okay? Final temperature. 24.5 degrees for the water. So what's the final temperature for the metal? It's the same, because they're both together in that same environment. There we go. Now, we're given the specific heat capacity here. For water is 4.18 joules per gram degree C. And the specific heat of X is what we need. So let's put this expression out here like this. 0 equals, what's the Q for the X? Well, the Q for the X is our unknown. All right? Let's do it this way. Mass, 45.9 grams. And change in temperature. Final minus initial. Okay? And then we add to that for the water. The water specific heat capacity is 4.18 joules, joules per gram degree C. The mass of water is 120. And the delta T, change in temperature, is final, 24.5, minus initial, 21.6. Okay? Now what we do is crunch the numbers. Subtract that one from that one, which will give you a negative number, correct? Let's do that. 24.5 and then 95.2 subtracted is minus 70.7 times 45.9 is minus 3,245 S. Okay? Then what's this term? Well, 24.5 minus 21.6 is 2.9 degrees times 120. And notice I didn't say anything about the units of measure because they're all right. Degree C, grams, and then joules. Joules is what you have left over. And then times 4.18, which is 1,455. Okay, so we need to put this on the other side, right? Makes it a positive. And then S is equal to this one divided by that one. 1455 divided by 3245. .45 joules per gram degree C. Okay, which one is that? 0.45. That looks like iron. Okay? That was 283. All right. Let's see. 285. For which of the following transitions does the light emitted have the longest wavelength? All right. Longest wavelength. So what are we actually talking about here? If the electron is transitioning from one of these levels to the other, and it's always going from a higher level to a lower level, which means what? It's going from higher energy to lower energy and gives off energy. So what do we know is the relationship of energy to wavelength? Well, we know Planck's equation. Planck's constant times the frequency. But it's not asking us about frequency, it's asking us about wavelength. Right? So if we substitute, what is this equal to? Speed of light. So if we solve for this one, that means that h times okay. So what does that mean? Energy related to this. So what's happening? As you transition from a higher level, from a higher orbital to a lower one, you give off energy. Right? So how much energy are you giving off? Well, it's related to wavelength in this term. In other words, as the amount of energy goes up, the wavelength gets shorter. Frequency gets higher, wavelength gets shorter, right? Because it's in the denominator. But the question was, longest wavelength. You want lambda to go up. You want long wavelength. So if this is long, as it gets bigger and bigger and bigger, what happens to the quotient? It gets smaller. So the energy gets smaller. You want the smallest amount of energy to get the longest wavelength. Smallest E implies longest lambda. So which one is going to give you the least amount of energy? Remember how the atom is constructed, the Bohr atom, that is. Right, there's your nucleus with a proton in it because this is a hydrogen. And this is level 1. Level 2 is way out here. Level 3 is a little closer. 4 is even closer. 5 is even closer, like that. Right. So where are the smallest jumps going to be? They're going to be out here between these guys. Anybody jumping to level 1 is going to give off a lot of energy and a shorter wavelength. So we need the smallest jump. 4 to 1 is way too big. 4 to 2, maybe a little better. 4 to 3, okay. 4 to 2 is bigger than 4 to 3. 2 to 1, that's still too big. 3 to 2, that's still too big. 4 to 3, I think, is the least amount of energy released, which means the longest wavelength. All right, 285. 287. Let's see, 345. Oh. Yep. I'm out of time. Let me see how much more I've got to go. 345. I haven't got too far to go, but this one right here, the Hess's law, is going to take a little work. I hate to split it into 3 sessions, so I'm going to finish this, and you guys can stick around if you want. If you can't, then come back and look at the video. And then Monday, I'll show up for the first 20 minutes. And I'm not going to count attendance at all from now on, simply because I'm not commanding you, and you don't have to show up if you want to use your time doing something else. But I'll be here for the first, say, 15 or 20 minutes class period on Monday, so that you can discuss any problems or ask any questions, whatever the case may be. But I'm going to finish this today. I think that's the best route to go. So here we go. 287, yeah. Which of the following is an incorrect designation for an atomic orbital? All right, so let's take it out. A, B, C, D, and E. And 1s, 6s, 3d, 1s, 6s, 3d, 1p, and 4f. Okay. Now, we could go in and say, all right, principal quantum number, angular moment, magnetic quantum number, angular momentum quantum number. No, the other way around. Principal, angular, magnetic, and spin. And just say how many can we have d orbitals there or s orbitals there? But I think the periodic table would be a quicker way. Wouldn't you? 1s. There's 1s, hydrogen. This one is allowed. 6s, go down here to 6. 6s, it could be cesium or barium, right? That's true. 3d, so here's 3. And you go across here and skip to 3p, but you go back to 4, 3d's right here, right? First, the fourth period through the transitions is 3d's. That's good. 1p, okay, 1s, 2s, no p's in sight. That's false. And 4f, right, if you go 4, you would get the 4d here, or if you go to 5 to 4d, but we need f's. Where do f's fill? Down here, right? So there's lanthanum, there's 6s. Lanthanum starts the 5d, but immediately goes down here to this group, 4f's. So that one is true. It looks like D is the only incorrect one right there. All right. How about 299? Oops, too far. $2.99. In the molecule XEF2, xenon difluoride, how many pairs of electrons surround xenon? And what's the molecular geometry? Okay, so we have to draw the Lewis dot structure. So xenon is a noble gas. It has 8 valence electrons. Fluorine is a halogen. It has 7 times 2 is 14, correct? So that means we have 22 electrons. So we put xenon in the middle, fluorine, fluorine, 2, 4 is 18. So we go 2, 4, 6, 8, 10, 12. 6 electrons left over. So we have 2, 4, 6. Okay? That's everybody. So fluorines both have octets, but xenon is 2, 4, 6, 8, 10. 10 electrons. It exceeds the octet. So that's why I don't have any double bonds in there. We don't need them. It's already got more than it needs of electrons. I go back to the question. What's the molecular geometry? Well, the molecular geometry, what's the most stable situation here? The most stable is to put the fluorines at the apex. By the way, 1, 2, 3, 4, 5, what's the electronic geometry around xenon is trigonal bipyramid. So xenon in the middle, you have a fluorine up here, oops, and a fluorine down here, and then you have lone pairs here. That's a trigonal bipyramid electronic structure. Molecular structure is linear, right? You know what? That's not going to give us an answer. If we do it this way, then the molecular geometry will be linear. But how many pairs of electrons surround xenon? It doesn't say lone pairs, does it? Just how many pairs? Well, there are 1, 2, 3 lone pairs, but there's also a pair here and a pair there. So that's 5. So it's 5 pairs of electrons. And then the molecular geometry is linear. Okay? So there you go. C should be the best answer. Okay. Now we get to use Hess's law. So what is Hess's law? Hess said that if you propose a chemical reaction that you want to study, and you want to find out something about its enthalpy, it's never been done before, you can take, since enthalpy is a state function, doesn't matter what route it takes to get there, we could stack together 2 or more different reactions, the enthalpies of which we know, and once we've manipulated the reactions so that when you add them together, you get your proposed reaction, then you also add together the enthalpies after they've been modified accordingly. Okay. So here's the equation. Let's see, 302. And that one's getting kind of weak. Put it over here. There we go. Okay, here's the target reaction. Calcium carbide, solid, plus 2 water, yields calcium hydroxide, solid, plus acetylene gas. This is the reaction that coal miners used to rely on in their helmet lamps. They put a few crystals of calcium carbide in there, put some water with it, and it would decompose spontaneously, produce acetylene that comes out the center of the lamp, but in the reflector, and they'd light it, and that's what they would use to see their way around in the dark. So we want to know something about the enthalpy of this reaction. Well, we've got these 5 reactions here, right? And we want to see, can we manipulate them? Well, let's see. We don't have calcium solid anywhere. We don't have graphite anywhere, but we do have calcium carbide right there. But this reaction is reversed, right? So we need to flip it. And that will give us 1 calcium carbide on that side. So this calcium carbide yields calcium solid plus 2 carbons, and I'm going to say Gr for graphite. So what's the delta H for this one? When you flip the equation, change the sign of your delta H. So it's positive 62.8. There we go. So that takes care of this one with this reaction. Okay, what's the next one? Calcium, oxygen, calcium oxide. We don't have any of that in there. All right, so let's leave that one. We might need it later. We'll come back to it. How about the third one? Calcium oxide, water, and calcium hydroxide. There's calcium hydroxide. And there's only 1 of them. So we can use this one as is. Calcium oxide solid plus water, liquid, yields calcium hydroxide solid. So we got this one and that one. And the value is the same as in the table, minus 653. Okay. How about the fourth one? Well, it's got acetylene in it right here. What if we go back and use the second one, right? Because calcium hydroxide is good, but calcium oxide we need to get rid of. So let's use this one as is. Right, there's 1 calcium oxide there, 1 here. So if we use calcium solid and plus 1/2 oxygen yields calcium oxide. Okay? And that we put that one in there for the sole purpose of canceling this one. Right? So, and we didn't change it out at all. Minus 635.5. Okay. So we're going to keep that one. Now we can go to the fourth one. Acetylene. Acetylene needs to be on the right. Right? And we need 1 of them. So we need to flip this equation also. So we need to put 2 CO2s and water on this side. And let's do it this way. 5/2 oxygen plus acetylene. I'm going to put it right down here. C2H2 gas. Because I want to put the value out here. So what's the value for delta H here? We flipped it. So change the sign. Plus 1300. Keep that one. Okay, so now we got this and this. Right? We've got a water here and a water there. 2 waters. So everything we need is there. But there's some things that we don't need. Right? This is only canceled out half of those. So now we got 4/2 or two oxygens. We got a calcium here and nothing to cancel it. Wait a minute. Oh, there it is right there. Calcium, calcium. All right, we can cancel this one, and that leaves us here with 4/2 or 2 holes. Okay. Carbon dioxide and graphite. What are we going to do with these? Looks like we're going to use this one. So this has got graphite on the left-hand side. Graphite's on the right-hand side here. So we can put that one in. We just need 2 of them. Plus 2 oxygens yields 2 carbon dioxide. Okay, what does that mean for our delta H for that part of the reaction? We doubled it, right? We multiplied the whole equation through by 2, so we double 393.51. 393.51 times 2. Still got the negative sign in front of it. 787.02. Okay, so we got 2 carbon dioxide here, 2 there. We got 2 graphites here. We got 2 graphites there. We got 2 oxygens here, 2 oxygens there. So it looks to me like that's it. Now all we have to do is add up the enthalpies. All right. I've already got this one in my calculator. So I'm going to take 1300 plus that, and they're all kilojoules, and so we don't have to change the units. And then 635.5 minus that one, and 653 minus that one, and 62.8 plus that one. So I get minus 712. Okay, what did I do wrong? Let's see, 62, 635, 653, plus 1300, minus 7. I must have hit the keys wrong. Either that or the answer's wrong. Let's check. Do it again. 62.8, 653.1 subtracted, 635.5 subtracted, 1300 plus and 787.02 subtracted. No, that answer is wrong. It should be 712. I get a negative. The negative says this is exothermic. I think that value is wrong. Yeah. That value is wrong. I mean, all you have to do is just add it up. Right? These two together are going to be about 1300. Gets rid of that one. So then you subtract this one from that one, still gives you a negative. Yeah, that value is incorrect. In fact, I'm going to edit it right now. It should be negative 712.82. There you go. So that was Hess's law. Now, don't forget how to use Hess's law, because in second semester, if you decide you want to take it, and if you've passed this one, then we expand on Hess's law into equilibrium, and we can combine equations to determine the equilibrium constant for an unknown equation. But there's a different set of rules for equilibrium equations than there are for enthalpies. All right, let's get this stuff off of here. Oh, Hess's law always gets messy. It'd be better if we could put this on a huge classroom whiteboard. Then we could kind of spread out. All right, let me get this out of the way here. No, there we go. Okay, 305. So we have this table that we need to fill in based upon the information that we're given up here. So let's construct the table. We've got molecule A, B, and molecule C. I'm just going to say A, B, and C. And we have 3 cross lines, cross groups. All right, this first one is going to be electronic structure. Second one's going to be what type of hybridization is it? And the third one is bond angles. Mathematical symbol, that means angle. Okay, so we're given this one. That's it. Now we got to do the rest of them. All right, consider 3 molecules. Molecule A has hybridization sp3, that's given, on the central atom. Molecule B has 2 more effective pairs, electron pairs, around the central atom than A does. So if it has 2 more effective pairs, what would B's hybridization be? We've used up all the S's and P's, you got to go to D's now. So it's D2sp3. All right. Molecule C is diatomic. Diatomic and consists of 1 sigma bond and 2 pi bonds. So what do we know about bonding? You got to have at least 1 sigma bond before you can have any pi's. So if it's diatomic, right, there's your sigma, and there's your pi, and there's your other pi. That means that there's a triple bond in there. And that also means that the molecule is linear, which means what for hybridization? SP. All right. Okay. Now we have the hybridization. What can we say about the structure? Well, we've already said this one's linear. All right. This one should be 2, 3, and 3 is 6. If you got 6 equivalent hybridized orbitals, what type of shape will that give you? Octahedral. And this one should give you tetrahedron. Okay? How about bond angles? Now remember, this is the outline shape. These are not bonds. So when you actually draw the bonds in there, for this one, it's 109.5 degrees. Bond angles, all of them. How about this one? Well, think about it. 1, 2, 3, 4, 5, 6. Yeah, that's like a square bipyramid. In other words, you have the square, and then you have up there and down here. Right? That's an octahedron. So what are the bond angles? Well, if you have the central atom here, then the only possible bond angles that you can have are between this one and one of these, which will be 90 degrees. Or you could have this one all the way across to this one, which would be 180 degrees. Or you could have this one to that one, which is another 90 degrees, same all the way around. So 90 and 180 are the only possibilities for that one. And linear is 180. No other possibilities. Okay. That's 305. Oops, that's it. So you'll notice here that you've got a solubility chart and a periodic table, polyatomic ions, useful information. There should be another, there it is, and all your equations and some constants. Oh, you even have electronic structure. So all of those should be available either in a single document, maybe multiple documents, in the folder with the final exam. So when you take the final exam, be sure and go in and print these out if you don't already have them. If you've got them already printed out, there's no sense in wasting ink. Just pull out those copies and you can have them there with you while you're taking the final. Okay, that's the last one. And we went about a half hour over. But this way, you don't have to come back on Monday unless you want to. Well, that red doesn't want to come off. Okay, any questions, comments? And the final, next week is not final week, the week after is final week. And I think I set your final date based on the schedule, which is kind of ludicrous. I mean, we're all Zooming anyway. So you got week after next to do the final. In fact, I think the way I've got it set up is once you have completed an exam, the next one in the sequence opens up. You can take it anytime you want. So if you're behind on taking exams, then you're not going to get to those later exams until you've taken the earlier ones. There's not going to be any hopscotching in this class. Okay. I didn't hear any comments or questions. So I'll be here on Monday for the first, say, 20 minutes, just to see if anybody shows up and needs help. If you need to come in later than that, than the first 20 minutes of the class, then just shoot me a text or an email, and I'll know to stay on long enough for you to show up. That won't be a problem. Okay, that's it. Stop the share.